16, we will continue on gallium arsenide MESFET from where we left in the last lecture. So, in the last lecture we just introduced the concept of MESFET and how the current saturates and how it works, but today we will go to short channel MESFETs which are of more importance to microwave applications, and beyond that we will talk about different kinds of MESFETs and architecture and fabrication, etc. Okay. So, over to whiteboard here. So, what we talked about in the last lecture was about long channel transistors, but if you have short channel, then your channel length modulation will kick in and you will have an output conductance. So, you see the current is not saturating, the current should have been saturating like that, but there is a slope here. The slope is called the output conductance, and this is not good because this will reduce your gain. Okay. Output conductance is not good because the current is not saturating, it is behaving more like a variable resistor than a transistor, and this is very difficult to avoid if you have a short channel device. Okay. So, there is a mathematics to also find the slope based on the hyperbolic field dependence, gate having two regions 1 and 2 that we discussed in the last lecture, but in general people have found out that an approximate relation of this output conductance goes something like L by H. Okay. So, you want this output resistance or the inverse of output conductance to be as high as possible. If it is infinity, it means the current is 100% saturating. Okay. So, to have this as large as possible, your L by H should be very large. This is called the aspect ratio, and the aspect ratio should be at least equal to 10. So, in modern electronics, for instance in microwave electronics, if you are looking at a gallium arsenide MESFET, say the gate length is around 0.5 micron or 500 nanometer, then the channel H should be no more than 50 nanometer, correct. The gate to channel distance should be no more than 50 nanometer, alright. So, that puts kind of a constraint, it should not be more than 50 nanometer. Okay. Otherwise your L by H will be worse and your channel control will be poor and your output conductance will shoot up. Of course, it depends also on your drain current, and drain current you have a certain range of drain current, certain application requires certain drain current. So, you may not have much of a window to design there, because the application or the systems people will need a certain drain current. However, what you have in your control as a device engineer is the L by H. So, your L by H should be high, you should always keep that in mind, and it becomes more difficult to maintain when your device goes to shorter and shorter gate length for higher and higher frequencies, then your maintaining aspect ratio becomes more challenging. Okay. So, this is important to understand about the concept of output conductance. Now, in a short channel device, the gradual channel approximation of course breaks down, and when I say short channel, the length of the channel or the gate is so short that the critical electric field at which the material breaks down, okay, multiplied by the length of the channel is much lower than the drain voltage, which means, sorry, when I say F critical, it is not the critical breakdown field, it is the critical field at which the carriers saturate. So, what I mean is that if I plot velocity versus the field F, then the velocity will rise and then saturate in material like silicon or in germanium. In gallium arsenide material, it will rise and then it will peak and then come down because of the intervalley effect or the gun effect. Okay. But if you can say this is your critical velocity, the F critical. So, F critical is the critical velocity at which F critical is the critical field at which the material starts exhibiting velocity saturation. If your length is short, such that this critical field times the length is much less than the drain voltage. In other words, the drain voltage you are applying is larger than the product of the critical field times the length of the channel, then you are talking about the carriers being in this regime, which is a velocity saturation regime. It may be a peak overshoot, but nevertheless the carriers are no longer in the linear regime. So, the carriers will travel at velocity saturation entirely below the gate, and in this case the carrier transport is independent of the low field mobility, but this is only below the gate. If you have excess region, but that is between gate and the drain and between gate and the source, if you have some region, in those regions mobility will still be important, because only below the gate you will have velocity saturation, not in other regions, not necessarily in other regions. Okay. So, in that case, let me remove this. Okay. So, what will happen is that in that case the saturation current can be expressed in a much simplistic manner. It is the width of the channel, the charge of the channel times the velocity of the channel, velocity of the electrons, which is V set. Very easy, no complicated equation. The Z is the W of course, and so the width of the device, I mean the charge on the device. Now, if this is from a different textbook, so instead of H they use this A is actually the H in the previous diagrams, okay, the total width of the channel. You can see that on the source side there is a certain depletion, but on the drain side of course there is a larger depletion. We explain why that is so. Now in this expression the charge that is available to carry, they take it as the Q times A minus WDS. WDS is this, which means A minus WDS is this quantity. So in other words, the current is basically taken as the product of the width of the device times the charge Q times this, which means it assumes a rectangular kind of a profile because it is taking A minus WDS. It is kind of taking a rectangular kind of a profile and times the doping and of course the velocity saturation. Why do they take the depletion width on the source side only, so that the channel opening is defined here? It is because towards the drain side lot of funny things happen. There is something called a dipole layer formation that I am not going to discuss in this course per se, but because if you remember there is a small, in the drain side of the channel the depletion goes like that and there is a small pinch off that is happening here, there is a small channel that opens here. Locally what happens is that your carrier density in a spot near that can actually become higher, the local carrier density can become higher than the background doping that you are giving. Okay, your carrier density can become higher than because you need to maintain, if you want to maintain higher current but the velocity saturation is constant, so your doping density is ND, the local carrier concentration will locally increase compared to the background doping concentration. So the field will become, the field will change its value, the doping concentration will change its value. Eventually what happens is that there is a region of higher negative charge and then there is a region of lower negative charge or a positive charge. So there is like a dipole that forms, and because of all these things that is happening on the drain side, it's a convention to take the width on the source side that defines the ID set, okay, and this is a very powerful expression because it tells you that the ID set does not depend on the gate length. In this case it does not depend on the gate length, okay, under saturation condition for a short channel device. Okay, it is a very unique situation. So if you take a transconductance of this and if you which means you take a derivative of the drain current with respect to the gate voltage, you plug in values etc., you get this expression, which is the width times the dielectric constants times the velocity divided by the WDS, which is this, which is fixed. Now epsilon by WDS is actually the CGS, which is the gate source capacitance. So CGS times velocity saturation times the width of the device gives you GM. So this GM does not depend on the gate length, which is unique in the short channel device. This GM also does not depend on VG because the gate voltage does not modulate this part, the WDS, which is the depletion width on the source side, is not effectively modulated by the gate. So the GM technically here is independent of the gate bias, which is very remarkable because it means that the GM is actually flat, it is constant, and it is very good for a linearity application. Your GM, if you have a constant GM over a certain voltage range, it means it gives you better linearity. Okay, if your GM is constant over a certain, which means if you plot the GM with respect to the gate voltage, the GM should stay flat like that. So the GM being flat helps in improving linearity because the gain is neither increasing nor decreasing. So different parts of an input signal will be amplified by the same amount, for instance. So it is a linear system. So this kind of a short channel MESFET can give you a linear performance because you have a GM which is independent of the gate voltage. But again, people do other more advanced tricks also, will come to that, to help improve this flatness of the GM, because only this may not help improve the GM as much, although theoretically it should, but practically there are more effects that come in terms of nonlinear resistances, channel heating, etc. So there may not be a completely flat GM practically speaking, okay. But in short channel effect, this is short channel MESFET, velocity saturation happens, and this is the basic idea of how the device works, okay. Now the breakdown of a MESFET is also very remarkable. If I take a silicon JFET, JFET is just like a MESFET except that you have a, instead of a Schottky metal, you have a p-type material to deplete the channel. In silicon devices with higher gate voltage, your breakdown voltage increases. You see, this is breaking down here, this is breaking down here. So this is the output characteristics, right, and this is breakdown. So you see at higher gate voltage, the drain voltage at which the breakdown happens increases. This is because you are basically compensating for the gate voltage. If you are applying a more higher gate voltage, you need to increase the drain voltage subsequently in the same proportion to maintain the same gate to drain voltage. Okay. So, essentially at a certain gate to drain voltage you have a breakdown. If your gate voltage is increasing, then your drain voltage also should increase to maintain the same VGD. That is what is happening here. Okay. However, in terms of gallium arsenide MESFET, this is not so simple. In fact, it is the opposite, which means typically with higher gate voltage you will actually get a lower breakdown voltage, and this is very remarkable. So, we have to understand that in a MESFET or even in any other FET, the gate metal which has the edge towards the drain has the maximum electric field, because all the field lines terminate there. All the field lines in the depletion region will terminate at the gate metal towards the drain side, facing the drain side. So, the field is highest at the edge of the gate metal towards the drain, we call it the drain edge of the gate, and when the field is highest, it is the point which is most likely going to start impact ionization and breakdown will happen. So, the gate drain spacing in a MESFET is critical, that is point number 1. Point number 2 is that the surface traps which is not present so much in silicon, because you have a silicon dioxide, excellent dielectric, so many of the surface traps, surface problems do not appear so much in silicon as they appear in 3-5 semiconductor, because we do not have a native oxide like silicon dioxide for a gallium arsenide or a gallium nitride material system. There is no biblical or a very sacred gate dielectric even today. That is why surface traps are very important phenomena, or they are sure to exist on the surface of gallium arsenide MESFET, and surface traps can actually modify the field. In some cases the surface traps can actually improve the gate breakdown, the overall device breakdown. Okay, we will see that. So, 2 points, one is the surface traps on gallium arsenide which do not exist on silicon, they modify the breakdown, they can actually improve the breakdown for a matter of fact. And secondly, the gate drain spacing, the spacing between the gate and the drain is critical, because that spacing is going to block the voltage. Now, that is all fine, but what is the reason why in gallium arsenide MESFET with higher gate voltage you have a lower breakdown? Okay. Gallium arsenide devices typically have higher currents than silicon. So, when you have higher currents, your local node temperature also increases, the lattice temperature also increases. Okay. When your temperature increases locally, because in gallium arsenide you have higher currents than silicon, your expected temperature in gallium arsenide is slightly higher, and also because the thermal conductivity of gallium arsenide is poorer than silicon. So, your heat is not that effectively dissipated in the substrate. So, your gallium arsenide has a higher local temperature than silicon. When you have higher temperature, your gate leakage increases. Why? Because as we shall see, the gate leakage in gallium arsenide MESFET, it is a reverse bias Schottky junction. It can leak through tunneling, which is roughly temperature independent, but it can also leak through thermionic field emission. Thermionic field emission is temperature dependent. So, with higher temperature of the channel, your gate might start leaking due to thermionic field emission, and if the gate starts leaking more, then it will initiate the breakdown earlier. Okay. You will have more carriers to come and start the avalanche. So, your impact ionization could start earlier, although impact ionization has a the breakdown due to avalanche increases with temperature, but in this case the gate current can actually leak into the channel and reduce the breakdown, and that is why at higher voltages, at gate voltage, okay, where you have more current, you have more reverse leakage, more temperature rise, you will have lower breakdown. This is the reason why gallium arsenide behaves different than silicon. Point number 2 was also about the surface traps that help improve in breakdown. So, what in this image you are seeing is the electric field. This is the electric field on this is 0 is the surface, and this is towards 0 is not the surface, everywhere is the surface, 0 is the distance from the gate to the drain. So, 0 represents the edge of the gate metal, this represents suppose the edge of the other side of this is the drain metal, and this is the gate metal, this is the gate metal. So, this is the gate drain spacing. So, you can see that if psi s equal to 0, psi s equal to 0 means that there is no surface depletion, there is no traps. Traps will lead to some surface depletion. If there are no traps, then there is no surface depletion. Then you see the electric field follows like this. It is a peak electric field comes here and it drops. It drops just here, it does not go all the way to the drain, and this point can break down. because it is high field. So, now we can assume that this reaches F critical, but this is not critical field for velocity saturation, this is critical field for breakdown. So, it can break down. Now, if the surface electric field is 0.65 electric field, electron volt, which means the surface traps have modified the pinning on the surface to be 0.65 electron volt, in which case the field profile will be changed by the surface traps, and you can see the field profile is something like that. So, it has, if this is the point where breakdown happens, then this has not reached that point, which means I can go to higher and higher drain voltage before this point reaches that point. It will go like that, it will go like that, eventually it will go like that, and it will break down. The area under this curve is the breakdown voltage. If the area has increased, it means breakdown voltage has increased. That means a psi-s of 0.65 electron volt, which means there is a certain trap concentration that has modified the surface pinning level. If this has happened, then your breakdown voltage improves. Okay. And also you can see, I will maybe remove this again. You can see that for a, oh, I kept it actually, sorry, I will delete it and then I will come it here. So, you can see that for a surface depletion level of 1 volt, the field at the edge of the gate is 0, but it suddenly spikes up towards the drain. So, that means this part will break down, the edge of the gate, sorry, the edge of the drain metal will break down. So, that surface traps are critical, and how do you control that? You cannot control this as much, but you can use passivation, field plate and other techniques to modify the surface field so that you can get higher breakdown. But this is precisely the same thing I said, gas MESFET has higher on current, high temperature, initiate breakdown. So, these are the different mechanisms for leakage. This is thermionic emission over the barrier that has a strong temperature dependence. Thermionic field emission is some part over the barrier, some part tunneling. So, that depends on temperature, and this is field emission which does not depend on temperature, it is just a Fowler-Nordheim tunneling that happened here. However, because gate leakage is dominated by this and also this at very high bias, overall there is a temperature dependence. With higher temperature your gate leakage will increase and that will initiate the breakdown. Okay. So, we have to understand that the Schottky gate in a gallium arsenide MESFET is basically a reverse biased Schottky junction. So, the gate leakage will contribute to breakdown if you do not take care of preventing the gate leakage. Okay. Now, there is a little bit of more math in this slide, but up till then I hope the things are clear. Now, the next slide that we are going is to talk about where in the MESFET channel the doping is not constant, but it can be say graded, or it can be any arbitrary doping profile. The doping can change as a function of the depth, say y. The doping can change as a function of y. It is not a constant doping everywhere, and that is called arbitrary doping profile. Why do you need that? We will see that. Okay. It may not be very extensively used in commercial devices, but it was still used and it still might be used because it can give you better linearity. That is the reason why an arbitrary doping profile has been championed to be it can cause higher or better linearity. So, this slide may look little bit more mathematical, but actually we do not have to memorize the math equations, just to understand a little bit. This gives you the potential variation inside the MESFET channel if there is a variation in the doping. So, NDY is the doping variation along the y direction, and if in a constant doping case this is just ND, but now it is NDY. So, this expression has come from some derivation, we do not have to worry. You can integrate this of course to get the current, and the current comes out to be the width of the device, charge, mobility, dielectric constant length, QA minus QWD. QA is basically the total charge in the channel, okay, in the absence of gate, in the absence of any depletion. QWD is the depletion, the charge stored in the depletion at any point x, for instance, when you have a depletion width of W, correct. QA minus QW tells you how much is the channel opening. So, if you can do some simplify around it and again integrate, you eventually come up with this expression. This is your total saturation current for a short channel device, okay, velocity saturation times the width of the device times the charge QA minus QDS. What is QA minus QDS? So, if this is your channel, okay, this is the total channel, this is the height of the thickness of the channel H, or here you call A. QA minus QWDS, basically it goes something like that. This is the drain, this is the source, this point is WDS. So, Q minus WDS basically means this point, and this is like a rectangle. So, I am talking about rectangle of this, the conductivity of this rectangle essentially. QA minus QWD, okay, is basically the conductivity of that rectangular region, conductivity of this rectangular region, conductivity of this rectangular region times the velocity of saturation times Z. If you take a derivative of this, you get an expression like that, okay. And you can see that this depends on the width, this depends on the velocity saturation, this depends on the epsilon, this depends on WDS also. And Gm by Cgs is velocity for any transistor, okay, whether it is HEMT or MOSFET, does not matter, MOSFET. The ratio of the transconductance Gm by the capacitance Cgs is the gate to channel or gate to source capacitance. This ratio represents the velocity of saturation, okay. So, a higher Gm by Cgs ratio means the material has a higher velocity, okay. In general, if the velocity is the constant, which is how it should be, a higher Gm also leads to higher Cgs, okay. So, just to maintain the constant velocity, this is constant basically, okay, that is all fine. But you see this term WDS, although we use WDS as this point, but in reality, as I told you, it is more complicated than that. In reality, essentially, since your Gm is basically your, you can say that this is your velocity of saturation times the dielectric constant times your W depletion. So, Gm can be constant and independent of gate voltage for a better linearity if WDS or the depletion region is independent of the gate voltage or it is constant, because velocity of saturation is constant, dielectric constant is constant. So, to obtain better linearity, we need a better we need a constant Gm. A constant Gm is possible when your depletion width is constant with respect to gate bias. What it means? It means that depletion width should vary very little with gate bias. So, if you change the gate bias from 0 to -1, -2, -3 volt, the depletion width of the channel should vary little, should change very little, okay. That is a very strange condition, by the way. If that happens, then your Gm will be constant for a short channel device, and this can be enabled by the graded channel. This expression, by the way, is the same for a uniform doping channel ND or for an arbitrary doping channel or a graded channel. It is the same expression, precisely the same expression, no difference. But the graded channel or you can say an arbitrary doping profile can help improve the linearity, and people have shown that experimentally also, by the way. So, what happens is that this is uniform doping, the doping is constant. This is a doping which is, this is the surface 0, this is the depth A, the channel A, this is your the area 0 and this is your A, this is the channel, this is your gate for instance, this is your source, this is a drain, okay. So, A is that, okay. So, your doping is increasing exponentially maybe, or as a power law, it is called power law doping. The doping density is continuously increasing as a power law from the surface towards the depth of the layer. Beyond that is your substrate which is insulating. So, this is your substrate here, okay. So, until the interface of the substrate, the doping is increasing in a power law. In this case, the doping is constant, which is what we have usually discussed. So, if your doping is increasing as a power law, then forget the math. What happens is that here you are plotting ID in a way, ID by some constant, you are looking at a ID which, if the Gm has to be constant, then ID has to be perfectly linear, right. If your Gm, because the derivative of ID is your Gm. So, if your ID is perfectly linear, like a perfect linear, then the derivative of that will give you a flat Gm or a constant Gm. So, if you are in your power law, if your n tends to infinity, if this power law if n tends to infinity, then you get this perfectly straight line, you see. This is the potential, you can say, this is the channel potential, forget about it, this is the channel potential, and this is, you can say, drain current, some representation of drain current. So, you can see this is perfectly linear. So, if your power law, if you can change it in an, this power law exponent should be as large as possible, you will get a flat Gm or a linear device. Similarly, they have a delta doping. This is your surface 0, this is at the interface A, this is substrate. At that interface, you have a delta doping, a very high doping for a small thickness, okay. In that case, if this is narrow enough, then you get this straight line. D by A equal to 1, which means D equal to A. Do you know what D equal to A means? D equal to A means that this point and this point are the same, which means it is one delta doping like that. In that case, you will get the perfectly linear ID, which means your Gm will be constant, and that is good for linearity, okay. if your D is halfway between D and A, then you get something like that, you know, your linearity becomes degraded. So, an arbitrary doping profile has, people can do this to get a better profile of GM, a flat profile of GM, and improve the linearity. People have experimentally showed that this kind of a doping scheme, you know, where your doping of the channel happens only towards the interface of the substrate and the channel. The rest of the channel from the top of the gate to the interface is very lightly doped or almost not doped. In that case, what happens is that your GM does not suffer, but your CGS becomes your CGS becomes lower, okay, and this helps in noise also. People have shown that this kind of a doping profile can improve linearity. People have shown this, that it can improve linearity, it can also improve noise performance. We will come to that later, but you know, when your doping is away from the top and is towards the bottom of the interface, then your linearity and your noise both improves. Linearity improves because you get GM which is constant. Noise improves because your GM by CGS improves. The GM is constant, but your CGS reduces, the gate channel capacitance reduces because it is a little far away. Okay, so the depletion, overall depletion is little more, you can say. So epsilon by D is less, so CGS is less, and that is why your noise becomes better. Okay, so this arbitrary doping profile is very useful for those kind of things, but again this is not this may not be widely used because it needs a little bit more involved material growth technique, but nevertheless this is a useful thing to learn. So from this point onwards we will move towards actual MESFET structures, how different types of MESFET structures have evolved over the last many decades, how to fabricate them, and what are the different smaller and bigger, you know, important things related to their different layers, how to improve breakdown, how to improve noise, how to fabricate them, etc., is something that we will take up from the next lecture. Okay. So thank you for your time, and this brings us to the conclusion of lecture 16. Okay.